jumping in the middle here because the iPad had a hiccup or something. So the pressure from the helium is going to equal the fractional composition. The fractional composition is just the percent divided by 100. So 80% becomes 0.8 times the total pressure. Well, 0.8 times 1 is 0.8. The partial pressure of the helium is 0.8 atmospheres. The partial pressure of the nitrogen is 20% over 100, 0.2 times 1, or 0.2. Does that make sense? So if we have a gas mixture that has 64% methane and 36% ethane, the total pressure is 1.44 atmospheres. What are the partial pressures? Well, the partial pressure was equal to the fractional composition. We really need like a, actually there is a variable for that, but they don't use it in this book, times the total pressure, P total. Well, let's abbreviate methane as an M. The partial pressure of methane is its fractional composition. What's the fractional composition of methane? 0.64, right? 0.64 times the total pressure, 1.44 atmospheres. .64 times 1.44. 0.92 atmospheres. What's the partial pressure of the ethane? We have 0.36 times 1.44. 0.36 times 1.44, 0.52 atmospheres. So in that gas mixture, the ethane is exerting a pressure of 0.92. Did I say ethane? I meant methane. There's so much alike. The methane is 0.92. The ethane exerts a pressure of 0.52 atmospheres. What do those add up to? They add up to the total pressure. Look at that. Any questions? If it was 50-50, half the pressure would be from one gas, half would be from another. It's whatever the relationship is here. If there's more of one gas, it exerts more of the pressure. Doesn't matter what gas it is, how big, how small the molecules are. The size of the molecules is irrelevant. It's insignificant compared to the volume of the gas itself. This leads us to Dalton's law of partial pressures. So the total pressure is equal to the partial pressure of each gas in the mixture. And we just looked at that and said, well, 0.92 plus 0.52 added up to the total. So if we have 1 atmosphere of air, we did these calculations with the nitrogen and the oxygen, 0.78 and 0.21. The argon is going to exert a pressure of 0.01 atmospheres, and you add those up and you get 1 atmosphere of total pressure. And this is the stuff we need for lab today. A sample of hydrogen gas is mixed with water vapor. So we've got a mixture here. We've got hydrogen gas and we've got water in the gas state, 2 gases. The total pressure is 745 torr. The water has a partial pressure of 24. So this guy's 24. What's the pressure of the hydrogen gas? What should we do? There's two gases. Together, their pressures make up the total. We just subtract. This is one of those things where we did all these complicated things and now this can't be that easy. It is. Tommy had 10 cookies and he gave 3 to Emily. How many does he have left? That's all it is. So how do we write that out? Well, Dalton's law says that the total pressure is equal to the partial pressure of each gas. So that's the pressure of the hydrogen plus the pressure of the water. And so that means that the pressure of the hydrogen is equal to the total minus the other one. So the total is 745 torr. The pressure of the water, we're told, is 24. So then we end up with 721 torr is the pressure of the hydrogen gas. Which of those two gases is there more of in that mixture? Is there more water or more hydrogen? There's a lot more hydrogen because the hydrogen partial pressure is much higher than the water because there's a lot more of it. This part in your textbook is really interesting, but we're behind in lecture, and so I'm not going to cover it. There will not be questions about it on an exam, but you should read it because it's interesting. We can do this question, though. A diver breathing heliox with an oxygen composition of 5% wants to adjust the total pressure so that the partial pressure of oxygen is 0.21 atmospheres. What must the total pressure be? What's this 5% about? 5% of the mixture is oxygen, right? So it's 5% oxygen. We know that the partial pressure of the oxygen is 0.21 atmospheres. We want to know what the total pressure is. Did we do anything like this with a percent? It was back a few slides. The partial pressure of a gas equals, let's just call it X, the fractional composition times the total pressure. Total pressure, fraction, that comes from the percentage. It's the percentage divided by 100. And this is the partial pressure of whatever gas we're interested in. So we could rearrange this, couldn't we? The total pressure of the gas is going to equal the partial pressure. We're talking about oxygen, so let's put O2 in there. The partial pressure of the oxygen. I don't think oxygen exert a partial pressure. Divided by the fraction of oxygen. What's the partial pressure? 0.21. What's the fractional composition? 0.050. We take 5%, divide by 100. So 0.21 divided by 0.05, 4.2. So the total pressure needs to be 4.2 atmospheres. Things like this are really important when you're scuba diving and you're breathing underwater and you can't just get out of the water real quick. There's a lot of chemistry involved with the mixtures of the gases and all of that stuff. So is anybody in here a scuba diver? No? They make you go to some pretty serious classes before they let you go out there, and there's good reason for it, because there's a lot of complicated things about it. It's a lot more involved than snorkeling. Okay, here's a picture of what we're actually going to do today. Collecting a gas over water. Gases are hard to deal with because they float away. You can't just put them in a beaker, right? They float away. So what we do to collect a gas is we'll take a container and fill it up with water, and we'll generate the gas in another container and collect it by bubbling it into this inverted container. Here it's hydrogen. As the hydrogen comes in, it pushes water out. But we can trap the hydrogen gas. So that's great. But the water in here is evaporating, and so up here we have a mixture. We're going to have water vapor as well as the hydrogen. So this is where we need to use Dalton's law of partial pressures, because we're only interested in the partial pressure of the hydrogen, and so we need to subtract out the pressure of the water, because we can't measure the pressure of just one gas or the other. We don't have a gauge for that. It turns out that the pressure of the water depends only on the temperature of the water that it's above. And so we can actually just calculate this. There's tables. I'll pull one up for you for lab. We need one that's a little more detailed. As the temperature increases, the partial pressure of the water increases. So we can just, if we measure the temperature of the water, we can look up the partial pressure of the water. So here's one last quick example. Hydrogen gas was collected over water, total pressure of 758 millimeters of mercury, a temperature of 25 degrees Celsius. What is the partial pressure of the hydrogen gas? Anytime you see over water, there is a mixture involved. Gas collected over water. Total pressure is 758 millimeters of mercury. The temperature is 25. Are we going to do a calculation with the temperature? No. We're just going to use it to find the right line on the table to look at. 25 degrees, the partial pressure of the water, and we call it vapor pressure. It's just a special name we have for it. It's just the partial pressure, 23.8. So the partial pressure of the water is 23.8 millimeters of mercury. What's the partial pressure of the hydrogen? Oh, you just subtract, right? Oops, I don't want to know there. It's the total pressure minus the water. So it'll be 758 minus 23.8. 758 minus 23.8. 734 millimeters of mercury. Any questions? We're going to leave this last section, even though it's short, we're going to leave that for the next exam.